Okay, it's 4 p.m. Okay, good afternoon. Welcome back, everyone, for the second day of lectures. Before we start, I have an announcement to make. Lecture notes are uploaded on the website, and I left the link in the chat. You can find it easily, and it will help you understand today's lecture better. And today's speaker is Professor Koenraad Schalm. He will be giving a simple introduction to APCTP and its application to condensed matter physics. Okay, so now we have Koenraad third lecture.
Okay, thank you so much, Myung-Yoon. So before I continue immediately, at the end of yesterday, there was a very good question. We finished with computing a 2-point function in a CFT using the Gkpw description in ADS. And there was a question is, how do you compute higher point functions? So the higher point functions go exactly the same as before. You just need to recall that if you solve a Dirichlet problem, we realized that in essence, the prescription in Gkpw that the field had a fixed boundary value that you identify as the source in the CFT, that is equivalent to a Dirichlet problem. That means the fluctuations of the field do not change. And if you look at your electrostatics books on boundary value problems in electrostatics, and you want to find out what the electrostatic potential is in the presence of a bulk source with a fixed boundary potential, then you find that the expression is as follows, where the following object is the Green's function. This is the Green's function, and this is the derivative of the Green's function. And so you just apply this to the ADS CFT prescription on how the partition function for the CFT in the presence of sources is related to the ADS partition function. And the idea was that you just substitute into the action, right, the on shell, in other words, the solution to the equations of motion. So let's consider a simple scalar field action where I now have a nonlinear term. I have an interaction, a simple phi cubed interaction, right? And again, what I did is I did one integration by parts. So I have the boundary term, and I have this term, which is proportional to the linearized equations of motion. So that means this solves the linearized equation of motion. So when I substitute this in, this will vanish, but these other parts remain. Now, the first thing you do is you do the standard trick as in quantum field theory. You write this as a derivative with respect to bulk sources J. And then you can actually integrate out the field. And then you find that this remaining partition function now has two bulk source terms, plus it has this standard boundary term that we already saw earlier. This was not present, this was present before, these extra terms remaining. But you also get a cross term between the boundary value of the field and the bulk source term. Okay, and now you just apply the functional derivative trick as you do in ordinary perturbation theory in quantum field theory. And what you will see is that for the 3-point function, the leading order term comes precisely when you take one vertex, right? And then you need to pull 3 curly j's, or in other words, 3 bulk sources down. And at the lowest order, actually, that corresponds to only pulling down 3 times this factor. And that is sort of graphically described here, right? I have 3 of these boundary values j, right? And they meet in a bulk point in the center, and then I have to integrate over all possible locations of that bulk point. And this is how you compute a 3-point function. Okay, and this combination of the derivative of the bulk propagator is sometimes known as the bulk to boundary propagator in ADS CFT language. But you should not confuse it with anything as if this is something new. This is something that you know from electrostatics. It's just the normal derivative of the Green's function itself. Okay, and in this way you can build up all higher point functions, and you sort of see, and this graphical description is that you get a sort of new version of Feynman diagrams where you include sort of the propagation to the boundary. This is not really new. This is like the S matrix type computations in quantum field theory, where instead of the external legs being truncated to get an on-shell S matrix element, now on the external legs, you have one of these bulk to boundary propagators, and you still have to do a remaining integral. And you can build this up all the way from 3-point functions to 4-point functions, right? And sort of this is graphically the notation. And the way you should think about it is, remember, ADS is a cylinder. And the picture that you have here is you're basically looking on top of the cylinder. So there's a vertex in the bulk, right? And then there are some propagators from the boundary to the bulk. If you look on the cylinder sideways, you get something like this. These are now incoming fields and one outgoing field, right? That propagate from the boundary inwards. They meet in the bulk and they propagate back out to the boundary. And this way you can compute, in principle, any order of higher point functions. In practice, 4-point functions are already hard enough, but people have done this. Are there any questions about this? No questions? Good. Then let me continue with the next aspect. So we stated the Gkpw rule, right? And in the Gkpw rule, as stated, it says that the full generating function of the correlation function operator O, or in other words, the generated by a source J, is equal to the path integral over the fields in ADS, where you equate the boundary value of the field with the source J. And the first thing we did is to simplify it out. We simply said that this path integral is dominated by the saddle point. And that allows us to evaluate sort of ADS on shell. But strictly speaking, or not just strictly speaking, in order to justify the saddle point expansion, you need to have a small parameter. In standard quantum field theory, that small parameter is the coupling constant, or H bar, right? That's the loop counting parameter. And it's the loops that give you the correction to the saddle point approximation. So a very good question at this moment is, yeah, it's all nice and fine that you evaluated the action on shell, but what actually is the small parameter that controls the saddle point expansion? This small parameter can be deduced from the canonical example of ADS CFT. This 2 here is a footnote. It's not CFT squared, just to make sure. Okay. So the canonical example, in other words, the first example of ADS CFT was derived from string theory by Juan Maldacena. This is the famous first example, and it equates n equals 4 SUN super Yang-Mills theory with type 2B string theory on ADS 5 cross S5. So here you see this lives in 4 dimensions. This is the ADS 5. Because this S5 is compact, you can compactify and consider this as a tower of Kaluza-Klein states. And n equals 4 SUN super Yang-Mills is a very special theory that happens to be conformal, right? Even though it is a Yang-Mills theory, and naively it looks like it has a beta function, that precisely has the matter content that cancels the gauge content to have a 0 contribution to the beta function, and has exactly beta function 0. So this is a CFT. And if you study this duality, the way it descends from string theory, or this equivalence, you find out that in the CFT, there's a combination called the Yang-Mills coupling constant times the number of colors. And this is equal to the ADS radius that we saw in units of the string length. Now, what is the string length? The string length is the dimensionful quantity that controls Newton's constant. So as you know, Newton's constant is in 4 dimensions is proportional to the inverse Planck mass squared, right? It has dimensions of length squared. In 10 dimensions, it has dimensions of length to the power 8. So type 2B string theory, which lives in 10 dimensions, naturally has a gravitational coupling constant which scales as some length scale to the power 8. And it's this length scale that appears here. So what right? So this means that the radius of RDR is there's a dimensionless parameter, which is the radius of RDS of ADS in units of the string length. And this dimensionless parameter is equated with this funny combination in the CFT. And then the coupling constant cell itself is controlled by the coupling constant of the string theory. String theory has an ordinary coupling constant. Now, the interesting part is that this gravitational or general relativity, which is we didn't use string theory to compute all the correlation functions in the CFT yesterday, but we used just ordinary general relativity. And ordinary general relativity works when the string coupling constant is small, clearly, because we just do classical computations. We do lowest order in interactions. But what also has to happen is that the curvature of space-time, and the curvature is precisely controlled by our ADS, has to be very, very small. Or in other words, the radius of ADS has to be very, very big, right? If you have a sphere, which is very, very big, then its curvature is very, very small. So the approximation where we used ordinary general relativity to compute this precisely works when this number is very, very large and this number is very, very small. And here you see why ADS CFT is duality. The first lecture, or the first part of the first lecture that I gave you. Because if this is very, very large, this combination has to be very, very large. And as I will show in a moment, it's this combination, G squared Yang-Mills N, that actually controls the perturbation expansion in N equals 4 super Yang-Mills. This is actually a general statement in quantum field theory that once you have a matrix valued fields, and I will show that in the next few slides, the correct perturbation expansion is not in terms of G squared Yang-Mills, but in terms of G squared Yang-Mills NC. Oh, okay. So let me now show how that works, right? So what I want to emphasize is that this CFT reorganization in terms of these two combinations, G squared Yang-Mills NC and G squared Mill, is natural for any matrix valued field theory. And actually it is the correct perturbation expansion that you need to know. So let's look and what are matrix valued field theories? Well, a classic example are non-abelian gauge theories, but you can think of some other ways of having matrix valued fields. All right, you can just construct it. But let's take a non-abelian gauge theory as the example. So non-abelian gauge theory has just a simple Yang-Mills action, where now the field strength is non-abelian, right? It has this nonlinear term right here. It still has the mixed derivative of the vector potential, but now you have not one vector potential, but you have NC squared minus 1 if you have SUNC, or NC squared if you have a UNC gauge group. And when you do ordinary perturbation theory in non-abelian gauge theories or Yang-Mills theories like this, right? You write down the Feynman diagrams, and in this case, the Feynman diagrams for the gluons. And the gluons are, well, in this case, I wrote a photon line, but it doesn't really matter. But the point is you write a single line for this object in your Feynman diagram. And if you study Feynman diagrams carefully, what you see is what they emphasize is the momentum flow in the system. It tracks the adjoint charge, right? There's a single index here, and there's a single index here. So it tracks the adjoint charge. The propagator tells you that the adjoint charge at the beginning of the propagator should be the same as the adjoint charge at the end of the propagator. Rather obvious, because this is the field that propagates. However, 't Hooft realized that for these matrix valued fields, you can also track the fundamental color charge flow. Actually, what you simply do is you change basis. As you know, this A is the basis of the algebra. And what you should do is you should contract this with the generators of that algebra, right? They're generically matrices. So you can simply contract this propagator with two generators of either the SUNC or UNC or whichever other gauge group you use with that algebra. And then if you do that, you notice that the propagator becomes as follows. This I index has to be equal to this index L, and this J index has to be index K. If you use UNC, if you use SUNC, there's a small correction to it, but let me focus on UNC. And you can write this in a Feynman diagram notation as follows. There's a color flow fundamental color flow to the left, and there's a simultaneous fundamental color flow to the right. And then again, there's a color index I that goes to color index L, and a color index K that goes to a color index J. And this emphasizes the way the fundamental color charge flows through a Feynman diagram. Of course, this is still a single field, so you have to write these lines close together. It's a single field that propagates, so the field has two indices, and in that field, the color flows both ways. And this is what's also known as the double line notation. And you can not just do this for the propagator, but you can also do this for the higher point vertices. For the 3-point vertex, you get something like this. And for the 4-point vertex, you get something like this. Okay. And if you then put this together, if you build then a generic Feynman diagram, remember, you always have these two lines together, you get something that looks as follows. It looks like you have built little tiles that are glued together. Every time you have a double line connecting to a double line here, connecting to a double line here, connecting to a double line here, that forms a small closed loop. And you can think of this closed loop as a tile, or in a slightly more mathematical name, as a face, which forms a pattern. And it's very simple to write down sort of what the strength is in perturbation theory of a generic diagram. A generic diagram will have a number of 3-point vertices, V3. It will have a number of 4-point vertices, but remember the 4-point vertex goes with G Yang-Mills squared. So the power of G Yang-Mills for a generic diagram is G to the number of 3-point vertices plus 2 times the number of 4-point vertices. And the real power of this double line notation is, as I said, is it tracks the fundamental color charge. And if you realize that every time you have this line, it tells you that the index here has to be the same as the index here, has to be the same as the index here, has to be the same as the index here, and it has to be the same as the index here, and then you have to sum over it. That means every single closed loop here gives you a factor of n. And that is precisely the number of faces that you have in this diagram. So a generic diagram will scale as G Yang-Mills V3 plus 2 V4 times NC times the number of faces in this diagram. Okay. Now there's a very nice identity that is very easily derived. It's very simple. You take an arbitrary diagram and you give every propagator, you count the endpoints of each propagator and the endpoints of each vertex. And if you have a gauge invariant operator, that means all these lines must close, otherwise the object is not gauge invariant. And that tells you that 2 times the number of propagators must be equal to 3 times the number of 3-point vertices plus 4 times the number of 4-point vertices. That has to be true for gauge invariant operators. Now, if you just substitute this identity in here, that means you can also write this as G to the power 2P minus 2V3 minus 2V4 times NC to the power F. And this was a beautiful realization by 't Hooft, because this object here, like I said, it's like a tiling of a 2-dimensional surface with a number of faces. And Euler had already realized in this 18th century that there is a mathematical identity that relates the number of faces to the number of propagators and the number of vertices. And the number of faces minus the number of propagators plus the number of vertices is precisely 2 minus 2 times the number of holes in this 2-dimensional surface, right? And holes counts the number of holes in the 2-dimensional surface on which you can span up the diagram. And what is meant by holes is you should think of the difference between a surface, a sphere and a donut. A sphere has no holes, right? But it's a beautiful 2-dimensional surface. But the surface of a torus or the surface of a donut is also 2-dimensional, but it has a hole in the center. And that's what's counted by this number of holes. Okay, so remember this generic diagram. Therefore, you see that goes precisely as 2 minus 2 to the 2h if you contract one of the powers of NC into G squared NC. This is the way to go diagram. the diagram. This is the generic weight of this is the weight of a generic diagram in perturbation theory, using that identity of Euler. And here is the example that I just mentioned. Here you have a two-dimensional, here you have a diagram that is very simple, and you can put this diagram on a sphere. So this is a very simple object where h is 0. And indeed, if you count the number of vertices here, there's 1, 2, 3, 4 3-point vertices and 1 4-point vertex. That gives you g to the power 6. And if you count the number of closed loops, there are 5 closed loops. So this goes as g to the 6th to the nc to the 5th, which you can rewrite by pulling one nc here as follows. And this is precisely a manifestation of this general identity that we just derived. But here you have a more complicated diagram, and I realize that it may not be clearly visible, but these lines do not intersect right here. This line lays on top of the other line. And if you look at this diagram, this can be put on a torus like this. And what you have here is you don't have, this is no vertex then, there's no connection here. So you only have 4 3-point vertices, so g to the 4. And if you count the number of loops, you have to be careful because this object right here goes all the way up, comes back here, 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 closes here. That's one loop. And so in fact, there's secretly only 2 closed loops in this diagram. So this goes as g to the 4th to the nc, which I can rewrite by making the combination g squared n to some power 2 as g squared nc to the power n0. And this is indeed a diagram that you can span up on the two-dimensional surface of a torus, okay, where h is 1, the number of holes is 1. And the point is that this is really what, if you have any matrix valued field theory, this is the way the system reorganizes itself. It has a double expansion, right, in terms of g squared nc and nc. It does not have a good expansion in g squared, right? Because if nc is large, then you can have diagrams that are lower order in g, but are higher order in the second expansion. And in particular, it means that you see that there is if the number of holes is large, then there's a 1 over nc term here. So if nc is very, very large, then the sphere, or if you add quarks in the diagram, the so-called planargram dominates. And this is also therefore called the planar diagram expansion. Although strictly speaking, for a planar diagram, you need quarks. Now I have drawn here lots of Feynman diagrams, right? And you clearly see that if the more g squareds I have, the more lines I have in here. And so there's an expansion in 1 over nc. And there's a second expansion in this combination g squared nc. And conventional CF quantum field theory, or the conventional planar diagram, of course, still has that g squared is small. Otherwise, I cannot do the corresponding algebraic expression that corresponds, compute the algebraic expression that corresponds to this Feynman diagram. The loop integrals would just be way too complicated. So in conventional quantum field theory, you have a large n expansion. But then on top of it, you take this combination g squared Yang-Mills and c very, very small, so that you have a low number of propagators and vertices in the system. However, we have just seen that through the canonical example of ADS-CFT, that there, because I needed a large curvature, this combination g squared and c had to be very, very large. And this is the duality statement that is underlying the power or the interest or the beautiful discovery of ADS-CFT. This is what allows us to access the strongly coupled regime of the ADS theory, of the CFT using the ADS theory, okay? Vice versa, of course, the CFT in its perturbative regime accesses the strongly coupled regime or the strong curvature regime of gravity. And this is why this object is a duality. It describes the same physics, but from 2 very different perspectives. And that's really the power of ADS-CFT. Now, when you do these correlation functions that we just computed earlier, the 2 and the 3-point function, they are to a large extent fixed by the symmetries in the CFT. So this expansion is interesting, but you could have guessed the answer simply based on symmetries. But as we will progress in today and tomorrow, we will see that we will start to deform the CFT and go away from the CFT fixed point. And then all of a sudden, this becomes miraculously powerful insight into strongly coupled matrix valued field theories. And that those are predominantly, of course, non-abelian gauge theories. Are there any questions? Okay. So we're now going to do a first step towards this generalization away from a very simple CFT answer. And the way we're going to generalize it is we're going to study the CFT, not in its ground state, but at finite temperature. Okay. Now, there's a very simple way we study the CFT at finite temperature, and this uses the conventional the conventional identification between the finite temperature partition function in quantum statistical mechanics, which is just traced to the e to the minus beta h, where beta is the inverse temperature, and a quantum field theory in periodic Euclidean time with the Euclidean time, this should have been a tau, identified with tau plus beta, where the quantum field theory is defined by its path integral, which is a trace over e to the minus ith. So if you make this Euclidean and you identify it periodically, you get an identification between this finite temperature partition function and the dynamical QFT. So what does this tell us? Well, that means that if I want to understand this in its dual anti-de Sitter description, well, we're solving saddle point equations, so we need a solution to the ADS Einstein's equations. And what we know now is that we can identify the space-time where the CFT lives as the boundary of that ADS. And what we when we apply this map, what we need is that this boundary is now not a Minkowski space-time, but somewhere or another it's a space-time where I have Euclideanized the time direction and made it periodic. So what I needed this space-time asymptotes to, if I take global ADS and D sphere, but now not times R, but times a circle, which is period, which has radius beta, sorry, which is circumference beta in Euclidean time. Or if I take a Poincare set of coordinates, it's just R to the D minus 2, which is the spatial coordinates times Euclidean time. So this is the extremely simple idea how to construct the CFT at finite temperature. What we simply do is we try to find an object which is a solution to Einstein's equations, right? Because that's what the identity says. I need a space-time with a positive cosmological constant, but the boundary space-time where the CFT, sources of the CFT lives, should be Euclideanized and made periodic in Euclidean time. And the solution to this is actually very well known. This is the ADS D minus plus 1 Schwarzschild black hole, right? Which has the following metric. There's a ds squared, and I've changed, this is Poincare coordinates, where now not the boundary is at z is 0, but the boundary is at r is infinity. And that's because this makes it easy to recognize it when you compare it to the ordinary Minkowski Schwarzschild black hole. The only difference is this overall factor, which now doesn't go like 1 over z squared now, but it goes as r squared, because r is infinity is now the boundary, and r is 0 is the deep interior. But the other two parts, there's this emblackening factor f of r in front of the dt squared and in front of the dr squared, is very similar to the ADS Schwarzschild black hole. This capital L should have been a capital R, my apologies. This is the ADS radius. There's one crucial factor is that I've written here in Poincare coordinates, And the blackening function is of the following type, where R naught characterizes the horizon. That's precisely where f of r is 0. And if you recall, that's precisely what defines the horizon, is when the GTT is equal to 0. Now, how do I know, or why could you have guessed that this is the solution to this puzzle that it asymptotes to Euclidean time? And the reason is that is as most of you know, a black hole at the quantum level is known to have a temperature. So there's already something like a finite temperature in. But to compute this temperature, Gibbons and Hawking realized that the black hole actually is a manifestation of precisely this identification between the quantum partition function in quantum statistical mechanics and the dynamical QFT. And in fact, it's now very well known as the most convenient way to compute the black hole temperature. And so let's do that, right? And how do you do that? So to compute the temperature for any generic static black hole metric, in other words, it's a black hole which is constant in time, it always has a form like this, where I have a coefficient, and so there's a generic static and also a homogeneous and isotropic black hole. In other words, the G does not depend on the spatial coordinates x, and it's static, and it doesn't depend on the time coordinates t. It only depends on some radial coordinate r. And then the most general metric that's compatible with those statements is as follows. I have a universal gxx, which is the same for all values of x as a function of r. There's a GRR divided by r, and there's a GTT r. And as you know from the Schwarzschild black hole, in order for this to be the right solution, I've written this as G inverse RR, but I could have also written it at GRR down. And Gibbons and Hawking realized that the easy way to compute the temperature of this black hole, that means that GT of R and GRR have a single 0, that's the location of the horizon. You can use this identification of going to Euclidean time. So what you simply do is you Wick rotate to Euclidean signature, where Euclidean time, tau, is I times t. Then you get a Euclidean metric, which looks as follows. So this is still the GTT. The only thing that happened is this minus sign has changed. Now you assume that there is this, that you have a black hole metric. So there's a single 0 in GTT near the horizon, and there's a single 0 in the inverse GRR. Okay, and GXX is regular at the horizon. So you expand these composed metric like this, and you zoom in on the near horizon metric. So near horizon, this object will look as follows, where these are the derivatives of these functions, right? But they're evaluated at the horizon itself. And now you define a new variable r. This is not the ADS radius, this is a new variable r, which is the following combination. And what this simply does is it changes the effective coefficient of dr squared into unity, okay? And r is, as you see here, is 0 at the horizon. So in the new coordinates, you evaluate g8x at the coordinate 0. And the d tau squared also changes. It changes in this rather complicated way when you do this coordinate transformation. But the key part is that you realize that there's also a capital R squared that appears here in front. And now if you ignore this part, this is all anyway regular, you recognize that this is something that looks very close to a polar coordinate system. This is just the radial direction, and this acts like the angular direction in a two-dimensional polar coordinate system. Now, the insight of Gibbons and Hawking is that the origin of this polar coordinate system should not be singular. And that's very simple, because the horizon, as we know, is a coordinate singularity. It's not a physical singularity. Nothing special happens at the horizon. That also means that in the Euclidean version of this space, nothing special should happen. right? It should be a regular point. It should not be a singular point. It's probably easier to see it the other way around. Suppose this were a singular point in Euclidean spacetime, then if you would Wick rotate back to Lorentzian spacetime, that singularity would not disappear, and therefore the horizon would turn out to be singular, but that's not the case. So there's a unique condition for this point R, capital R0, to not be singular. That is precisely if this is in fact is the origin of polar coordinates, because you know that the origin of polar coordinates is not singular, right? You can just choose, go back to Cartesian coordinates, and then the coordinate singularity has disappeared. But we know exactly what that's the condition. That means that tau must be a proper angle, right? And it must be a proper angle with periodicity 2 pi. Well, tau times this combination 1,4 G prime TT G inverse RR prime. That's the combination that should have a periodicity 2 pi. Okay, and so that is what you insist. And this periodicity is then directly identified with the inverse temperature of the black hole. Because here you see that the black hole insists that the Euclidean version of its spacetime has a periodic Euclidean time. And in fact, if you go deep, and this was the insight of Gibbons Hawking, if you go deep into the original calculation of Hawking, you see that he secretly, the appearance of the temperature is related to precisely this Euclidean identification. So for an ADS Schwarzschild black hole, you find now that the temperature T, that's 1 over beta, the periodicity, is equal to this combination here. And if I relate that back to the original coordinates, it's this combination here, where this, and that you can evaluate to be this combination, where this D is the D of taking the derivative with respect to R, and this D is the dimension, the number of spatial, the number of dimensions in the CFT for ADS D plus 1. R naught is location horizon, and capital L squared is the radius of ADS. So we have now computed the temperature of this ADS Schwarzschild black hole, and it's precisely related to the periodicity in Euclidean spacetime.
Excuse me.
Yes.
Is it you're trying to save tau from being singular? Is the only way to save it that it would be periodic, or is there no other option?
As far as I know, that's the only way to save it.
Okay, thank you.
Okay. Now let's use this. Let's use this insight that we've learned about ADS black holes. So it means that to study the CFT at finite temperature, we should study the corresponding ADS theory, not in vacuum ADS, but in the black hole solution to ADS, right? Remember that black hole solution is just a simple solution to vacuum Einstein equations. It's the non-trivial solution to this system. Okay, and let's try to do something with this. Let's study something interesting in the CFT. Now, it's actually a little bit difficult to do that, because an extremely important characteristic of a CFT is that if you put the system at finite temperature, because the CFT itself had no intrinsic scale, the moment you put it at a finite temperature, there's nothing to compare this temperature with. And it actually means that the finite temperature dynamics of a CFT is actually just a single phase. There's now a dimensional parameter, but since this dimensional parameter cannot be compared with any other dimensional parameter, you just get a single answer, right? And it's essentially the answer you get by placing the system in a compactified Euclidean time. So if you need if you want some interesting sort of finite temperature dynamics, or in other words, some thermodynamics, you need at least one other dimensionful parameter. And then you can, because then you can have something where you can have a high temperature phase. That's when the temperature is high compared to this other scale. Or you can have a low temperature phase where T is small compared to this temperature. Now, you may say, but wait a second, right? I have an ADS scale in the problem. Yeah, but the ADS scale under normal circumstances, does not appear in the CFT. We've shown that the ADS scale is in units of the string coupling constant, is actually related to this G squared Yang-Mills n. So that's a dimensionless parameter. But there is a way, nevertheless, to get the ADS scale in an indirect way into the as a scale in the CFT. And that is if you take global ADS. Because global ADS, remember, the boundary is not flat space-time, but the boundary is a sphere. And the sphere has its own radius of curvature. That is, of course, related to the radius of curvature of ADS from the defining equation of global ADS. But that means that the CFT, which lives on this, you can always think of the sort of living on this boundary. The CFT also lives on this space with a curvature R, and it can know about it. Actually, you have the same story again here. If you study it at 0 temperature, it barely knows about it because it doesn't know about a scale. But at finite temperature, it will absolutely know about the fact that it's living on this sphere. And that is what we will show now, but we won't show it from the CFT perspective. We will show it through the ADS computation. So for that, we need the, remember we're studying this at finite temperature. For that, we need now the ADS Schwarzschild black hole, but not the ADS Schwarzschild black hole in Poincare coordinates that we had a moment ago, but we need the ADS black hole in the global coordinates. And it's a somewhat more complicated, it's a slightly different solution because you have to take into account what happens to the curvature, what is the contribution of the curvature of this sphere. This is the solution. This is the global ADS black hole, where now this emblackening factor or the warp factor has a slightly different form than before, where this omega d is this combination, which is expressed in terms of the volume of the boundary sphere in d-1 dimensions. Okay. Now, that's one solution that you have, right? But you can also simply consider global ADS. Remember, the time direction was just the time direction that goes around for right. And I could just naively, blatantly make that time direction periodic. That is another solution. That is a solution called thermal ADS, right? And essentially, it's nothing more than the black hole solution where you put the mass of the black hole to 0. Indeed, if you put m to 0 here, you recognize this as the global ADS solution. With the only thing is that I've Euclideanized time and artificially made it periodic. Okay, so there are two qualitatively different solutions which have a periodic Euclidean time in global ADS. There's the thermal ADS solution with a temperature simply set by whatever periodicity I've identified time with. And for m is not equal to 0, when you have a black hole solution, I also have a periodically identified time, but it's now not independent. It's related to the mass of the black hole. And the mass of the black hole sets the size of the horizon. This is called R plus now. Okay. So that is the two solutions. And now you can understand what we're trying to do, right? If there are two solutions.
Sorry, I missed the point. I think I have a question.
Sure.
This asymptotic geometry is a sphere, so we get some scale which is related to length, and
yes.
But if we have some planar black hole, then we had planar, so Minkowski space in the boundary of ADS. Then how do we get some length scale in that case?
You don't. That's the point. So if you do if you study the CFT in ADS and Poincare correction, there is no phase transition. Well, I will come back to that at the end of it, but the simple answer is no there, right? This is precisely the argument why I'm now going to global ADS. I need another scale to have a phase transition.
Okay.
And there are many ways. Actually, tomorrow we will introduce a scale in a different way. Yeah. But we now introduce the scale in this particular way.
Okay, I see. Thank you.
No, but so it's a very good question. You need this other scale, and if you do this in Poincare coordinates, you don't have it. Okay.
Okay.
Okay. So we have two qualitatively different solutions, and if you have two solutions, right, there's of course only if you would study the system at finite temperature, right, there's only one real solution, right? And in thermodynamics, the way you determine which is the real solution, that's the solution that's thermodynamically favored. That's the solution which has the lowest free energy. Now, we are studying quantum statistical mechanics, and in quantum statistical mechanics, we know exactly what the free energy is. It's -1 over beta times the log of the partition function. And now we can use ADS-CFT because we know what the partition function of the CFT is in terms of the action if we study the classical, semi-classical saddle point limit where G squared Yang-Mills and C is large. That's just equal to the 1 over beta times the on-shell action. So to understand which solution is thermodynamically favored, what we should do is we should compute the on-shell action, the value of the on-shell action for both, and determine which one has the lower value. That's the one that's thermodynamically favored. And this is not so hard because we're studying pure gravity. This is the action for pure gravity, and I realize I have a small notational thing. This R is the Ricci tensor, and this R is the ADS radius, right? So I should correct my notes to and send you a new version to avoid this confusion. But that means that the on shell, you just have that R is dd plus 1 over the ADS radius squared. And when you substitute this back in, you just find that the on-shell action is nothing but 2d divided by the ADS radius squared times the volume of the space-time. Okay? Now you have to be a little bit careful how to compute this volume because ADS is like a hyperboloid, right? It has formally had as an infinite volume. But of course, what we're going to do is we're going to compare two solutions, right? So if we take the difference in the correct way, that infinity should drop out and we can get a finite answer between the two objects. Okay, so let's do that. The on-shell action is naively infinite, and there's another object that we need to be rather careful with is remember that in this thermal ADS solution, we've just periodically identified time, right? But we want to compare the temperature of this periodic time with the temperature of the black hole. Now, when you compare two temperatures, because that's the object that we want to do, we compare which free energy at which temperature is larger than the free energy temperature, you need to express them in some units. Actually, you need to express them in the same units, right? So we're going to actually put in a unit, and this unit is going to do two things for us. It's going to make the naively infinite on-shell action finite, and it also will give us the unit to relate to two temperatures, okay? So we do this in the same way that we did it in the last lecture. We're going to put a cutoff radius at epsilon, okay? And that will make the volume finite as a function of epsilon. What it will also do is it will allow us to relate the periodicities in space-time. And it's very easy. That's just the way time is measured by a local observer who sits at the radius epsilon, okay? And that is easy to see from here. If you look at the local observer in Euclidean time tau epsilon, which is a distance epsilon away, if you're in thermal ADS, this term is not here, but then you get a small time delay factor, which is related to epsilon squared divided by r squared. So if I include that time dilation factor, this is the time dilation factor on the thermal ADS side. Yes.
But thermal ADS does not have the horizon.
Nope.
So how we incorporate this periodicity in this calculate the temperature of thermal ADS?
So we just put in the periodicity by hand.
By hand.
Yes.
Okay, okay. Thank you.
You just make the time Euclidean, right? And then you simply by hand say, oh, I'm going to make it periodic. Okay.
Okay. There is no logic kind of why we put this periodicity there.
No,
Remove single.
it's a solution to the Euclideanized Einstein's equation, and it's kind of trivial because the Euclideanized Einstein's equations, they really don't care whether this tau is periodic or not for thermal ADS.
Okay, thank you.
It just doesn't appear, which is just the same statement that a single circle, right? A one-dimensional circle has no Ricci, no Riemann, or no Ricci, or no curvature, and that's why it doesn't appear in Einstein's equation.
Okay.
Okay.
Yes.
Yeah. But of course, on the black hole side, right? This periodicity is not arbitrary. It's forced on you, as we saw by the Gibbons-Hawking calculation, by the size of the mass of the black hole. Yeah. However, because we now have put it in a cutoff, right? You do have to be careful. There is still this, once you move a little bit inward in the radial direction, there's still this time delay factor, time dilatation factor, which in the black hole is related to, it's again related to this emblackening factor, but at the cutoff radius epsilon, it's of this type. So if you want to insist that this observer who sits at the location epsilon measures time and therefore measures temperature in the same way or in the same units, you have to insist that these two quantities are the same. Okay, that means that its unit is the same, right? And this is a subtle ingredient, but once you have the subtle ingredient, the computation is now very easy, because remember the on-shell value of the action times is just the volume of the ADS space-time times d over the radius r squared. So now I can compute the difference between the two free energies. Okay, so here's the computation for the thermal ADS part. Remember, this should have been a tau. I've just identified this with a periodicity beta. I have this cutoff in the radial direction, and I have this integral over the d-1 sphere with the volume factor r to the d-1. Oh, and I subtract from it now the free energy for the black hole, which is the same, which is now integrated to the black hole temperature. That's the periodicity here. And the subtle difference is that, of course, now the R integral starts from the horizon radius up to the cutoff. And if you just stick this in here, right, this is not so difficult to compute. What you find is the following expression. And the most important part is actually this term up here, the R ADS radius squared minus the size of the horizon squared. Because all the other terms are essentially positive, right? So this term tells you which of the two phases is dominated at depending on the temperature. So remember that the temperature scales linearly with R plus, right? So for R plus is much, much larger than the ADS radius, right? This is negative, and that means that the black hole phase has the lower free energy, and that's the one that's thermodynamically preferred. On the other hand, if R plus is much less than R, right, then you have a thermal ADS is the one that has the lower free energy, and that is the one that is thermodynamically preferred. Now, what I've put here is I've put two comments behind what these phases are. I've said that the black hole phase corresponds to a deconfined phase, and the thermal ADS phase corresponds to a confined phase. And this is a separate computation that you can do in ADS CFT, we know that in gauge theories, confinement and deconfinement can be diagnosed by computing the expectation value of a Wilson loop, right? The scaling of the Wilson loop energy as a function of its size tells you whether you're in the confined or the deconfined phase. If it's linear, you're in the confined phase, and if it's not linear, you're in the deconfined phase. And this is a computation you can also do in ADS-CFT. We don't do it here, but this is the one that allowed people to identify the black hole phase with the deconfined phase and the thermal ADS with the confined phase. So this shows you this phase transition in the system.
Sorry, your metric
Yeah.
was d plus 1 dimension, right? So if d is 1, I cannot see from this what happens.
Yeah. So this does not happen if d is this is ADS d plus 1, and ADS 2, right, which is when d is 1, has a very special role, which actually will come back tomorrow. So these things do not apply to ADS 2 or even ADS 3 is also
yeah.
right. So ADS 3 it also doesn't apply. This applies really to ADS 4 and higher.
Okay. Yes, thanks.
Yeah. Okay. Are there any further questions?
I have a question.
Yes.
So you consider CFT on a curved spacetime such as S1 times sphere.
Yeah.
So there may be a trace anomaly of energy momentum tensor. And does the trace anomaly depend on the two phase of CFT?
The trace anomaly.
So I think you consider a CFT on curved spacetime.
Yes.
So my question is,
well, the trace anomaly is dimension dependent. It's a good question, but I don't think it. I don't think it contributes to this calculation to lowest order. And I mean, the trace anomaly is not exactly topological, but it's pseudo topological. And so where this scales with the volume of the SD minus 1. So in that sense, I think it's subdominant, but I'm guessing right now.
Thank you.
Are there any further questions? I noticed that I'm in the same position as yesterday, that this was my lecture for the first session, but I really enjoyed the question sessions that we had at the end of the lecture now. So I propose that people ask questions about this, and I can answer them for the next half hour.
Professor, I have a question.
Sure.
Hello.
Yes.
How do we compute the temperature for thermal ADS?
Well, the temperature for thermal ADS is you literally. It sounds a bit trivial, but here's thermal ADS. Thermal ADS has M is 0. So this is just then the metric of global ADS, where the only thing I've done is made tau Euclidean. And then I can by hand just make it periodic with whatever periodicity I want. So the temperature is, you just choose the temperature directly by choosing the periodicity of space-time. I mean, in the black hole, you also choose the temperature, but that's by tuning the mass of the black hole, which sets the horizon radius, which in turn sets the temperature.
Now,
But again, you simply have a,
previously you showed about the how to compute the temperature for ADS social black hole case. Is there similar formalism for this thermal ADS?
no, but you don't have to, right? I could have presented, that would have been very confusing, but I could have presented the black hole temperature computation the other way around. I could have said Hawking told us what that the black holes have a temperature, and if they have a temperature, that must mean that their Euclidean time is periodic with some temperature b. And then I can ask the question, what is the corresponding mass of the black hole that gives me that temperature? And then I would have also had simply that the dial which changed the temperature is my periodicity in Euclidean time.
Okay.
If you understand what I mean.
Yes. Understood.
Okay, and so maybe that resolves the issue, right? You're think really of a very ordinary experiment, right? I have temperature as a dial, right? I can change the temperature at will, right?
Yes.
In the thermal ADS case, the only thing it changes is the periodicity of Euclidean time. In the black hole case, it also changes the periodicity of time, but at the same time, it changes where the horizon radius is and the effective mass of the black hole.
Yes.
And then what I do is if I would start at the very high temperature phase, which is the black hole phase, right? If I would dial it down, right? The moment the horizon radius becomes the same size as the radius of the sphere, right? That's the same as the ADS radius. Then you would see all of a sudden that the system would want to undergo a first order phase transition to this thermal ADS phase.
Okay, thank you.
I have a question.
Yes.
So for this free energy calculation,
Yes.
so we don't have to consider the counter term or something like, it seems that free energy calculation is basically calculating one shot action and naively, so I just
so I avoided that, right, by taking I'm comparing to free energies, right?
Mm-hmm.
So so the counter term, right? Normal counter terms in this quantum field theory are related to the UV, right? In other words, they don't care about whether you compute this at finite temperature or not, right? So these counter terms will be the same in this one and this one, right? So they essentially cancel. If you want to compute the free energy sort of without it, you have to be very careful, right? In this particular case, that's a difficult counter term to determine.
And one more question is so is it free energy correspond to some Helmholtz free energy or some Gibbs free energy?
Could you repeat your question?
So there, in the thermodynamic free energy, there are many different free energy, right?
Yes.
So, but which free energy correspond to this object? I mean,
this is the free energy in the canonical partition function. Canonical ensemble.
oh,
Tomorrow we will do it in the grand canonical ensemble.
okay. So at which point we could know whether this free energy is canonical ensemble or grand canonical ensemble in this calculation?
Well, at this moment there's no object that has any charges, so sort of the grand canonical and the canonical are the same.
Oh, okay.
Yeah.
Thank you.
And the reason why it's the canonical is very easy, right? We're comparing objects at fixed temperature, not at fixed energy.
Yeah, thank you for answer.
Welcome. Yeah. Any further questions?
Excuse me.
Yes.
Will you explain a little? I mean, is there a direct connection between this Gkpw rule that you talked about and this HKLL bulk reconstruction method?
Which
Will
method?
you talk HKLL, Harlow, Leibowitz?
I'm afraid I'm not familiar with that.
Oh, okay, so you don't talk about bulk reconstruction from like field theory CFD data in your lecture.
Oh, no, I'm not going to talk about that.
Okay, thank you. So,
No, I don't know the specific paper, but I do know what these people are trying to do. I can say one word about that. Okay, what they're trying to do. I mean, it's interesting and deep, and it's related to this first part of the lecture, where remember what we said is that the classical ADS, right, the saddle point expression in GR works if the radius of ADS is very large in string units, but this is the strong coupling expansion in the CFT, right?
mhm.
But you can ask the following philosophical question. Suppose this G squared Yang-Mills NC is not very, very large, but it's large but a finite number. Okay. What does the gravity side then look like? Right? We know GR works if I make that finite number infinitely large, and then I have a beautiful geometric description in terms of a dynamical metric that's governed by Einstein equations, right? But suppose I make it again not infinitely large, but large and finite. How should I think then of geometry? How should I think of what that object is? Okay, and so what the general philosophy of that program is to try to understand how space-time and the gravitational description emerges from the CFT. But you're going to even make it more drastically. What if G squared NC is finite, but not even large? But if it's tiny, then there's definitely no ADS to be found anywhere, right? I mean, there's just, right? You should just you do this Feynman diagram expansion. Yeah, but some and other, this Feynman diagram expansion, even at a small but finite number of G squared NC, somewhat knows that eventually out of this emerges, and literally in the physics sense of emergence, a space-time description. And what the philosophy behind not just Harlow but several people is trying to do is how can you understand the emergence of space-time, and can you already identify geometric structures even for finite G squared Yang-Mills NC? Okay, and the lectures here focus very much on how do I learn things about the CFT from the gravity side. But this turns the duality around. This is how can I learn things about the gravity side from the CFT? Right, and one of the deep insights of the last, I would say, 5-6 years, but I will not address that in these lectures, is that it's interestingly enough, sort of the entanglement information in the CFT that seems closely related to describing the emergence structures that in the infinite G squared Yang-Mills NC limit correspond to geometry, right? That's what's called this bulk reconstruction story.
Can I ask another naive question? Sorry.
Yeah, sure. That's why I'm here for.
So this partition function in the boundary and the partition function in the bulk, so they are in two different, one dimension higher, one dimension lower, strongly correlated, weakly correlated. But for example, is there any connection between the partition function between two gravity sides, like ADS4 and ADS3? Is there, do you like know any connection? There's no connection.
Nope.
Okay. Okay, thank you so much.
You're welcome.
And I have a question about what you
Yes.
said in yesterday lecture.
Yeah.
You calculate one point of function. I mean, you gave some explanation about boundary value problem, usually boundary condition using. So, I mean, if we consider Neumann boundary condition, that how can you relate? I mean, leading behavior of scalar field or sub-leading behavior of scalar field A and B, and how do we get some expression of one point of function? Yeah.
There are contexts in which you use a Neumann boundary conditions in ADS CFT. Well, the short answer is that if you consider for O not a scalar operator, but if you consider for O a current operator, J mu, right?
Yeah.
In other words,
Yeah.
O is related to a conserved current and a global symmetry. If you would gauge that global symmetry in the CFT, that precisely corresponds on the ADS side to changing from Dirichlet to Neumann boundary conditions. But in general, these are not the standard situations that you discussed. I hope that answers your question.
Yes. Actually, I did research about, so in that case. So I mean, I added some boundary action Legendre transformation related to Legendre transformation. Yeah. So, but I'm not sure at the time. I thought I'm not sure how A and so I mean reading behavior of scalar field A is correspond to some source that then does B correspond to some fluctuation of that field? I mean,
your question is, if I use Neumann boundary conditions, do I still have the identification of A as a source and B as the response? Is that your question?
Yeah. How can it change? How does it change?
Yeah, then it becomes a little bit more difficult. I actually wouldn't know the answer off the top of my head. Okay, but I mean the Gkpw. I mean this identification of A as the source and B as the response, that just follows from the Gkpw description, right?
Yeah.
And there are other modifications. For instance, if you do what so-called double trace deformations on the CFT, also this identification of A as the source and B as the response becomes somewhat tilted, right? But at the end of the day, it's just this is the defining relation, and from that you can derive essentially anything. So my answer to your question would be is that the simple rule of thumb that A is the source and B is the response, if you look at the solution of equation motion, that is the standard situation. But there are situations where it changes. But in that case, I would always go back to the original Gkpw rule rather than to try to modify sort of the effective rule of thumb.
So that could you give some physical interpretation of that situation? just, I mean, just physical picture?
So I don't really have a good physical picture with it. I mean, it's just the at the end of the day, the generating function of correlation functions, that is the powerful tool that you start with, right? So by taking appropriate derivatives and being careful about taking derivatives with respect to the source term, you get the answer, right? And so this rule of A is the source and B is the response is just it's a shortcut of doing the careful calculation, right?
Yeah.
But therefore, if you run into a situation where it becomes more ambiguous, the best solution is to go back to the origin rather than to try to patch up the rule of thumb.
Thank you.
You're welcome. Any further questions?
Yes, Professor.
Yeah, sure.
Suppose one can construct the boundary field theory and construct any boundary field theory. In gauge field in the boundary field theory, can we relate something with the bulk side? Only gauge field.
No, that's a very good question. So I did not emphasize it, but the only objects that you can relate on both sides are gauge invariant variables, right? Sort of there's a lot of emphasis has been placed recently by Cyborg, but it's one of those things that is well known to people who know it well. That of course an object which is not gauge invariant can never be a good physical observable, right? Because a local gauge symmetry can simply change it, and a local gauge symmetry is a choice by anyone. So the good objects are always gauge invariant observables. And so also in the Gkpw rule, these operators O, if you have an underlying non-abelian gauge theory as the CFT, it only the gauge invariant combinations of that can be mapped to operators on the ADS side. So that's a very good question.
Thank you.
Yeah. If there are no further questions, then we have a break now.
Yeah, good. So let's have 1 hour and 10 minutes later. So I mean,
Yes.
we'll meet at 6:30 p.m. in Korea and maybe
10:30 in European time.
yeah, okay. See, and then we'll see you and
Yep.
then okay. Thank you very
Okay.
much.
Until then.